we're going to introduce you to two ways that we can visualize distributions of discrete random variables. And the first is going to be actually plotting the theoretical probability distribution, also known as the probability mass function. And the second one's actually going to be via simulation, where we use built-in functions in Python to randomly sample from a given distribution, and then we plot the results. And we'll see how these two are related. In particular, let's think about just the idea behind a probability distribution. So any random quantity has what we call a probability distribution. And that's all the possible values the random quantity can take and the probability it takes each value. So classic example is I'm going to let my random variable be the number of heads that I get when I flip a coin 10 times in a row. So possible values, I could get 0, I could get 1, I could get 2, I could get all the way up to 10 heads. Each of those scenarios have a probability associated with them. And in particular, we can calculate that probability exactly. We've done it in previous lessons, and we'll revisit it again in this video. But sometimes we have more challenging situations. So something more challenging than just the coin flip, in which case it might not even be possible to come up with a nice theoretical formula for the probability for each value. However, oftentimes in those cases, it is possible to simulate what we call random draws from a given distribution. So what does that mean? That means we're going to use built-in tools in Python to come up with a data set that represents what would happen if we randomly were drawing values out of a distribution that had some underlying theoretical probability associated with each value. So in this case, we'll look at all the observed values our data take, and we'll look at the proportion of times it takes each value and use that as an approximation for the actual theoretical probability. And the great news is that these two will converge. So the empirical distribution will be converging to the probability distribution as long as we take enough independent samples. And so we're going to see that in the notebook. We're going to play around with that mathematically and visually. So let's actually jump over to the notebook demo. All right, for this first part, I'm actually just going to walk us through how we can think of this for a distribution that we've already played with in our previous lessons. And so here's a basic discrete probability distribution. This is my random variable x. It can take on the values either 3, 4, 6, or 8 with these probabilities. So let's actually see how we can visualize this probability mass function. We know the exact probabilities for each value. So I'm not going to do any simulation. I'm literally just going to plot some bars that the bar centered on 3 is going to have a height of 0.1. The bar centered on 4 is going to have a height of 0.2. And so I do that by giving you the independent variables here, k, and their probabilities here in a list. And then I'm going to call these matplotlib figure and axis objects just because it makes it easy to start to manipulate. And I think of figure as more like a canvas that I'm going to be playing with, and axis are going to be the individual plots. Axis has some nice methods like bar and hist that make it easy to play with. So let's actually try the bar method here on this data. First you put your independent variable, and then you put your dependent. And I'll point out here if I plot these. So, okay, didn't run that one. There we go. All right, so this is looking pretty great here. The height is, again, the probabilities. Now, what I'd like to do is I'd really like these histograms to represent, I want the areas of these bars to represent probabilities. So to do that, I'm just going to make the width here be 1. And that'll just be more consistent with what happens to distributions as we move to the continuous random variables as well. So if I do that, now the area of each of these bars is equal to the probability of getting a given value here. So the total area adds up to 1. And then sometimes just for a visual, I will have the edge colors just be white so you can see where the bars start and end, but that's not imperative. All right, so here's the distribution. So we can plot that nicely with the ax.bar method. The other way we could do this is actually using an entire data set that had this exact distribution. So if I take some data and manually create it, let's say we're going to take 100 values and I'm going to give 10 of them a value of 3 and 20 of them a value of 4, I'm basically going to create a data set with that exact distribution. And that's what I've done here. And so when you have a data set like this, now I'm not, in order to get the distribution, I'm actually needing to plot a histogram because I want to bin this data and count, how many 3s do I have? How many 4s do I have? So now I'm going to use the ax.hist method, and I'm going to just input the data. And let me just show you if we just do this, what happens. Okay, so there's a couple things I want to do to make this plot look exactly like this one, so we're comparing apples to apples. The first is to notice this is not a probability mass function as it's shown. These are frequency counts, the number of times that these values are showing up in the data list. So to make it a probability mass function, I'm going to add density equals true. And so now what this is going to do is scale this so that the area of one of these bars is equal to the probability. And so you notice the area of this bar is 0.8 times 1/2, which is 0.4. But really, I would like this to be a true PMF function. I actually want the heights over here to correspond to the probabilities. I want the widths to be 1. So a little hack to do that is actually just to set my bins. I'm going to call these B, and I can set them. I know I want to start at 3. If I set it at 2.5, it'll help center these bins so that 3 will be in the center. I'll just go up to let's go to 10.5 by counts of 1. And then I'm going to say bins equal B. And now I have the correct height, the correct width. Everything's looking almost identical to above. I'll just add my edge color in there just to make it look a little fancier. And we have the same answer. So this is a second way that we could get this distribution. But in either case, this is the theoretical distribution. This is not an estimate. This is not a simulation. This is the distribution of this particular random variable. I'm going to contrast that now with simulating draws from this distribution. So that's the next thing we could do, is I could say I would like to randomly pick numbers 3, 4, 6, and 8 with these probabilities. So over the long run, 10% of the time I'm going to choose 3, 20% of the time I'm going to choose 4, over the long run, right? And that's really what Python has built in when I do NP random choice. So here I'm going to simulate 100 data points. These are simulating like 100 random draws from this distribution. So let's just look at it here. Let me actually. All right, so here's 100 random draws. Now, because it's random, I'm not expecting with 100 that I will have exactly 10 3s or exactly 20 4s. I mean, I might, but it's not required. Definitely as I get larger and larger with this sampling, I'm going to be approaching these probabilities. But even like, let's even do it with 10. So, right, like I don't even have any 3s here, but that's okay. It's still the idea of sampling 10 different data points from a distribution of this. Okay, so now we're going to plot this. Let's actually plot this one. Great. So this is what we mean by the empirical distribution. We're getting it via simulation, but in theory, I could also get an empirical distribution when I just go out and sample a bunch of people from some population, and I assume there's some theoretical distribution that, their data lies in, and I'm going to be sampling empirically. And in theory, the more I sample, the closer this is going to look to the actual theoretical distribution. So let's see this. Let's do 100 now. Okay, so we're getting almost identical, pretty close here to there. I think we're a little bit higher on 0.8 on this one, or on number 8. Now if I go to like 1,000, oh, we don't need to print it out. Yeah, now we're basically identical. And that's the idea. The idea is if we're sampling from a distribution, eventually if we sample enough, then our empirical distribution is going to look almost identical to the actual underlying theoretical distribution. So in the next video, we're going to try this with some common distributions. We'll do the binomial and the Poisson. So I would recommend that you continue with this workbook or this notebook. Try some of these exercises on your own, and then you can open the next video to check your work.